Alright, so how's it going? Welcome to Hurricane 2018 video lecture series. Hashtag no Saturday class. I just made the hashtag sign. When I said hashtag, I can't help myself. I'm just so with it. This video, this like 40 seconds, is not going to age well. So that's the thing I should have thought of. Anyway, we're going to do the introduction to alkenes, and we're just going to go and see how far we get. I'm going to try to make this all like nomenclature and a little bit of theory and not really get heavy into reactions, because I want to kind of introduce reactions to you guys in person. All right, so we're going to talk about here initially what is an alkene. So I don't know why we're on slide 2. Good job, me. There we go. There we go. All right. We'll talk about what an alkene is. So an alkene contains a carbon-carbon double bond. Right, so something that looks like that. So here is our double bond. All right, so this is different than an alkane, which we talked about previously, right? We learned how to name, right? Alkanes contain only, that's not a letter. I don't even know what happened there. Sorry, guys. Contain only carbon-carbon single bonds. So the difference, right, is the presence of this. So this CC double bond. So that CC double bond can kind of be anywhere in your molecule, and it is still an alkene. Right, so if we want to look at how we refer to this, right? So the double bond, that carbon-carbon double bond, right? So right here, right, you will see it referred to as an alkene, right? Just this group, like, oh, that's an alkene, right? You will also, it'll also be called a double bond. That's typically what I default to. I'll just call it a double bond, right? You'll also see it called an olefin, which is an older term. Or it can be referred to as a vinyl group. So all of these terms are interchangeable for just a single carbon-carbon double bond in a molecule. So it can be an alkene, a double bond, an olefin, or a vinyl, I should say vinyl group. We want to be all the way proper here. All right, vinyl group. So this is how these get referred to. I typically will say double bond. I might sneak an olefin in there if I'm feeling fancy, but not much more than that. So alkenes are functional groups. Right, so you should know this because I made you learn the name of it as a functional group. But also, it's where reactions happen. So if you have a molecule, it's got stuff going on, an alkene, and you want to do a reaction, most likely you're going to react with that double bond. So in this molecule, the double bond is the most reactive group, right? So that's where you're going to see reactions. So alkenes are an example of a functional group because there were reactions happen. There were function happens for these molecules. All right. So we're going to talk about alkene structure. Right? So an alkene, so double bond, it's made up of two bonds. There is a pi bond, there's a sigma bond, which is the normal carbon-carbon single bond that holds carbons together in things like butane. And then there's a weaker pi bond that generates that the second bond in the alkene. So if we look at it, right, so if we have a double bond, right, we can kind of say that this bond here is the sigma bond, and this bond here, that's our pi bond, right? So the sigma bond, this is a strong bond, and the pi bond is a weak bond, right? So if we look at the structure, well, we'll do the structure in a second, right? So if we look at an alkene simply, right? Alkenes are flat. So the carbons that make up your alkene, so in this case the carbon, I'm going to draw it in, the carbon here and here, those are in the same plane. Now, every group attached to those carbons, and this H, this carbon, the first atom attached to this carbon, so this carbon, this hydrogen, and this carbon, those are all in the same plane as the double bond. So basically all of these atoms with red dots, all sit flat on the plane of effectively your screen, right? So those all sit flat and don't come up or out of the board. Now, once you get past that first atom, so out here, that atom is free to move. It can be up or down. It's not confined to being in the plane of the double bond, but the red dot atoms are. All right. The carbons of an alkene, so let's do another alkene here. So now our alkene. All right, we're going to make it simple here. So these carbons, the carbons that are in your double bond, that are part of the double bond, these carbons are sp2 hybrid. So a little Gen Chem throwback here. Right, so that means there's one s orbital plus two p orbitals used to make the bonds, and that leaves an unused p orbital, and that p orbital is used to make the pi bond. right? So if we wanted to keep kind of track, so we have 3 total orbitals, right? 1 s and 2 p orbitals, and that gives us our sp2, right? And we have 1, 2, 3 sigma bonds, sigma, 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 and then our pi bond, that comes from our p orbital that we didn't use. So it comes from the p orbital that wasn't hybridized. All right. So the bond angle of what? There should be a drinking game you guys start, like whenever I bring up like a window I don't want to bring up, or I fight with a little like color changey thing. You should just like, I don't know, drink, do a shot of soda or something. You know, we don't promote drinking. Speaking of, do a shot of soda here. It is super weird talking to an empty room. Super weird. Right. What I was saying before I got distracted with drinking games is right here, this bond angle from here to here is 120 degrees. So that is always the bond angle for an sp2 hybridized carbon. So these red dot carbons that are sp2 hybrid, their bond angle is 120 degrees. Now I've talked about the orbitals a little bit. I actually want to show you the orbitals and how those kind of interact a little bit. So just go up, see, drink, that. Oh my God, that can't be, someone will die. Can't do that actually. So let's just look at a simple alkene, right? We've got our sigma bond, sigma, which one was sigma? No, no, this one's sigma now. Here's the bond, now dog. Sigma bond, pi bond, all right. So if we look at the orbitals that are responsible for this, at least for the pi bond, so we've got our sigma bond here. Whoa. All right. I'm going to draw in a carbon here to kind of illustrate. So here's our carbon here and here. So coming out of those carbons are, you know, so I've got the hydrogens here. I'll draw those in. Okay. So right now I've got all of the atoms that are bonded to that carbon using the sp2 hybridized orbitals, and then there's this p orbital. You remember the p orbital kind of looks like a barbell. I need to art professor, so you know this is as good as we get for a barbell. So this is our p orbital. Right, so p orbital. Now remember, the p orbital, the top up here and down here, that is one orbital. So this whole side is one p orbital, this whole side is the other. So there's a p orbital on each carbon that is not being used to bond. Those p orbitals are able to overlap. The top lobe overlaps and the bottom lobe overlaps. So you get, in the overlap of the top bond and the bottom bond leads to the formation of one double bond. So this overlap plus this overlap equals one pi bond. Okay, we're going to try to make that a word. One pi bond. There we go. So you have the p orbital up here and the p orbital here. So both lobes, the upper lobe and the lower lobe, they overlap and give you your pi bond. So you got this sigma bond in the middle, right? And that is our strong bond, right? And the reason this sigma bond is strong is that results from like end-to-end overlap of the orbitals. So let's give you an example here. Right, so here's what the orbitals look like to make a sigma bond. So here's a carbon, have an orbital come out. Here's another carbon, have an orbital come out. And you have this good area of overlap right here in the middle, right? Where those two carbons can really get a good grip on each other, right? So I liken this to if you're hanging off a cliff, right? You want someone to really grab a hold of your hand really strong, right? So you're like latched on so you can't fall. So that's what a sigma bond is. This is two carbons have latched onto each other, they've really got a good grip. When you make a pi bond, the reason the pi bond is weaker is instead of getting this good end-to-end overlap, what you kind of get is kind of hard to draw, is you get an edge, the overlap here, this is an edge-to-edge overlap. Right? So it's kind of more like this. Right, so you don't get that same good large overlap. You get this edge-to-edge overlap. Right? So this is kind of so if you took your hands and you like locked them together, right, and held on tight, it's hard to pull them apart. Like if you just kind of wrapped your finger, like curled your fingers around, like interlocked your hands, you can't pull them apart, right? That's a sigma bond. The way I think about pi bond is you took your hands, had them facing away from you, and just kind of like laced your fingers together. So your palm was on the back of your hand, you just had your fingers kind of in between your other fingers, right? That's really easy to break. Right? I'm actually doing this for an empty room. Humor me in your dorm room or your apartment, hold up your hands and just kind of stick your fingers inside each other. And you can see that there's resistance, right? There's a bond there, but really if you pull hard at all, it's going to break. But if you lock your fingers together, if you take your hands and you just kind of curve your fingers and like hook them together, right, and you pull, it doesn't break. That's the sigma bond. So the pi bond is weaker because of this edge-to-edge overlap, as opposed to this nice, strong locking together end-to-end. Right? So what that leads to is when you have some reagent, right? This is we're gonna start the transition into anemia in a second. But if you have a double bond and you have some reagent, right? Something that can react with the double bond, right? And you're gonna add your reagent. We're gonna call it HX for right now. And you're gonna add X on one side, H on the other. Right? The bond that you break, right? You don't break the sigma bond. The sigma bond is not reactive. It's really strong, right? You break the pi bond. So you've got your pi bond and your sigma bond going into this reaction with whatever reagent HX, and what you get coming out of the other side is you keep your sigma bond, right? Because that sigma bond is strong, right? Those carbons are latched onto each other and can't break apart. But that pi bond, that weak edge-to-edge interaction, kind of the first sign of like trouble, you know, that bond will break. Basically, it's like every one of your high school relationships. The first sign of trouble, gone, right? Off to go hang out with someone else. That might just be me. I might just be a little bitter. Well, that would imply I had high school relationships. Oh, this is getting deep. Right? So you're going to keep that strong pi bond. Right? It's going to keep that strong pi bond, and then we're going to break. We're going to keep the strong sigma bond. Strong sigma bond stays. Weak pi bond gets broken when we react with reagents. All right. Hopefully we're doing all right. And if you're not, you can pause. That's power of the internet, man. Power of the internet. The internet for more than just memes. All right? So, we're going to talk about naming alkenes. So alkenes, since they're a functional group, like an alcohol or an amine, so they get a suffix. So what we end up doing is we replace, right on this? Oh no, powers, no, there's no power here. How good? Shots. So we're gonna remove the ane from our hydrocarbon name and replace it with ene. All right, so and we're gonna number just like we number like when we had an alcohol or something, where we're gonna make sure that we put our number between the names. So let's go to some exemplones, por favor. All right. So remove ane, add ene, right? So if we look at this, it has 4 carbons. 4 carbons is butane, but since this has a double bond, it becomes butene. So I want to leave a space, butene. So we're going to put a number in, and we're going to number this just like every other suffix. We're going to number it to put the lowest possible number in the name. So this will be but1ene. So here, right, so we've got our longest chain. And you're probably already done with it as I'm like fiddling with my stuff. Is 1, 2, 3, 4, 5, 6. So it's going to be hexene. We're going to have hexene, and we're going to have methyl group as a substituent. And so we're going to number to give the ene the lowest possible number. So of course the way I numbered this was backwards because I'm a bad person, right? So we're going to number it this way: 1, 2, 3, 4, 5, 6. Right? So we're going to have 5-methyl hex 1-ene. Right? We can also have double bonds in rings. Just troll you. Right? So this is a 7-membered ring. So we're going to have cycloheptene. We're going to have a methyl group. Now I put the gap in there, but I don't need it, right? Because we're starting with a ring. So we know that since it's a ring, our suffix, our ene, is going to be at carbon 1. But there's 2 carbons that can be carbon 1, right? We could go, this red carbon be carbon 1, or, or this blue carbon be carbon 1, right? We're going to pick the red carbon because that gives us the lowest number for the methyl group. So if we pick red, we get 1-methyl cycloheptene. If we pick blue, we get 2-methyl cycloheptene, and we want to always have the lowest possible numbers in our name. Since it doesn't matter which one we start at, because our alkene is the lowest possible number, we are going to pick the red number. All right, so here, again, we have a ring with a double bond, cyclopentene. So we know that we're going to have number 1. And we have a methyl group again, because methyls are easy to draw. I swear that says methyl. There we go. Right? Now this one's a little trickier. Right? When you start numbering, you always number across the double bond. So your double bond, the 2 carbons in your double bond always have to be R1 and 2, right? So what that means is if I start numbering here, right? Because our alkene is at 1, right? You have to number so the other carbon of your alkene is 2, 3, 4, 5. Wow. Wow. They say a good craftsman doesn't blame his tools. But I'm not a craftsman. This pen sucks. Alright. There we go. Let's try to get a 5 in there again. It does not look like terrible. Boom, there we go. That's like a classic Sesame Street 5. Alright. So I have to number 1, 2. I have to number across the double bond. Right? Now if I go the other way, if I start here, I can go 1, 2, 3, 4, 5. So if I do that, again, I have to number across the double bond. I start here, and I have to number this way. Using the blue numbers, I get the lowest possible number for my methyl group. So my methyl group is 3. There's no way that you can number that your methyl group can be on carbon 2, right? Because your alkene always has to be number 1 and number 2. So the lowest number you can get for it is 3. Deep sigh. So how would we name this? Right, this will be cyclohexene. And I have 3 methyl groups, so this will be trimethyl. Right? So we know that one of our 2 double bonds here or here, one of our 2 alkene carbons is going to be number 1. So if it is this carbon, so if I go 1, 2, 3, 4, 5, 6, or if it is this carbon, 1, 2, 3, 4, 5, 6. Right? So you always want a number to get the lowest possible numbers in your name. So if we pick the blue direction, we end up with 1 methyl, 3 methyl, 6 methyl. End up with 1, 3, 6. 1, 3, 6. If we pick the red numbers, we get our lowest possible number becomes 2. Right? So we end up with 2, 3, 6. So we're going to pick the blue numbers because that gives us the lowest possible number of 1 for our methyl groups. So, just another one for fun. So here, our longest chain is right here. Right, you want to make sure you pick the longest chain that contains your functional group, in this case, a double bond. Right, so this will be 1, 2, 3, 4, 5. Oop, gotta give myself space because I'm not in a ring anymore. There we go, we done fixed it. Right, and then we're going to have an ethyl group. And then a dimethyl. Right, and so we're going to number to give our alkene the lowest possible number. So we're going to number this way. 1, 2, 3, 4, 5. So we're going to have 1. Dimethyl is going to be 2, 4. Ethyl group is 3. So that's our basic naming. There are some, like with the fact that we have a group on our we have our alkene. There are different positions relative to the alkene have names that come up a lot when we're talking about reactions. So just kind of having the lingo is important. So there's vinyl or vinylic carbons and allylic carbons. So if we look at just a simple shots. Again, have soda or some other non-alcoholic beverage. All right. We have a double bond. The carbons that are part of a double bond, so here and here, these are vinylic carbons. Or just sometimes just vinyl carbons. Right, these have the double bond. So they are the carbons that are double bonded to each other. Our vinylic carbons are vinyl carbons. And then we have the carbon bonded to a vinyl carbon. This is an allylic carbon. Right. This is the sp3 hybrid carbon. Bonded to a vinyl or vinylic carbon. So you have more than one allylic carbon. So this carbon, so here, here, and here. These are, get that filled in there. These are all allylic carbons. They are attached directly to a vinylic or a vinyl carbon. Right, and then these are our vinyl carbons. They have like the memory of a goldfish. Like I changed slides and I'm like, what color do I make the allylic carbons? What color were the vinylic carbons? Sorry. As I often say, don't get old. Don't get old. Stuff stops working. It's awful. All right, so we're going to kind of swing back into naming a little and a little bit of stereochemistry here. And we're going to talk about isomers with alkenes. So the real big takeaway is that double bonds cannot rotate. So however your groups are oriented around your double bond, that's how they're going to stay oriented. They do not get to rotate like a single bond. Right? So that leads to isomerism, and it leads to stereoisomers. Okay, we're going red because I'm not going to go back. Now I'm going to go back. There we go. Okay, so we have alkenes do not. Okay, we're out. Let's see, can we just agree that doesn't say donut? But no, I should probably fix it. Alkenes do not rotate. This leads to stereoisomers. All right? So all alkenes have two forms, right? So for simple alkenes that are di-substituted, right? So you have cis and trans. So cis is the non-hydrogen groups. Are on the same side. Trans, non-hydrogen groups are on opposite sides. Right. So, for example, this is cis, right? So we have our two hydrogens. I'll draw those in red. Have two hydrogens here and here. They're on the same side. The non-hydrogen groups are on opposite sides. So they're on the same side, and the non-hydrogen groups are on the same side. And then we have trans. Trans, the hydrogens are on opposite sides. And the groups that are on the double bond are on opposite sides. Right, so we have cis and trans. So you can't go from cis. There's no way to get from here to here. This cannot, come on. Right, if you have the cis isomer, you are stuck with the cis isomer forever. When you have the trans isomer, you're stuck with the trans isomer forever. Right? Because the double bond cannot rotate. So trans, as a general rule, is lower energy, more stable. Right? The reason for this is kind of straightforward. Right? In the cis double bond, this group and this group are close to each other, there's a steric interaction. That these two groups are close enough that they bang into each other, their electrons hit each other. In the trans isomer, these are far apart. Right? I was trying to relate this to when you were growing up, you had brothers or sisters, right? Cis is when you were stuck in the car and like your parents had like a sedan, like you're in like a Toyota Camry, right? And you're just smushed. You're cis. You are smushed beside your brother or sister, and it's like 4 hours to grandma's house, and they're just touching you the whole time, right? You are close enough that there is repulsion, there is interaction, and you are not happy, right? And then finally, your parents get a minivan, and you got that third row of seats, right? One of you gets to sit in the back, and one of you gets to sit in the middle, and you don't have to touch, you don't have to interact. That's a way more stable situation. No one's starting to turn the car around or anything, because you're far apart. You don't have to mess with each other. Cis, those groups are smushed together in that little Toyota Camry, and you're just like, I hate it, get away from me. Right? Trans, those groups are far apart. Don't even have to know the other one's there. Right? So trans is way more stable. So cis and trans are examples of geometric / stereoisomers. Right, this is one of our kind of examples that we did for stereoisomers. Right, trans, cis. If you weren't worried about the cis and the trans, these are both 2-butene, right? They have the exact same name. The only thing is you have to differentiate the cis and the trans isomer in the name, which we'll get to in a second. All right, so nomenclature and just a little bit more here. So we can only have, so I've already stated that they don't interconvert. So if you have a mixture of cis and trans, you can separate them. They have different boiling points, different polarities, different solubilities. They are relatively, they're not easy to separate, but they can be separated. Whoa. I know, man, technology's killing me. There we go. The one doesn't rotate, and they can be separated. Cis and trans can be separated. Terminal double bonds do not have a cis or trans isomer, right? So terminal bond is just a double bond on the end of a chain. So, all right, let's look at, all right, so this is a terminal double bond. There we go. It's a terminal double bond. Right, so it's at the end of a chain, and you have two identical groups. These two hydrogens are the same. So when you have the same groups on your double bond, right? Same groups on the same carbon. There's no cis or trans possible. Right? So that's a terminal double bond. You only have cis and trans. Shots. You only have cis and trans. Alright, apparently I didn't want to change colors. We're just dealing with that. How we live our lives now. In internal I did not realize how much I rely on the fact that you guys can't see when I make a mistake because I'm standing in front of it. in class, but now it's just like, as soon as I mess up, it just like pops up on your screen. It's like, wow, I'm not very good at this. Right, internal double bonds, right, in the middle of a chain. Right, so those are in the middle of a chain. Those can have cis and trans. So we decided the molecule is cis or double bond is cis or trans by comparing the hydrogens. Right, so cis H on each vinyl carbon on the same side. Trans, you have an H on each vinyl carbon. On opposite sides. Right, so okay, that was probably my fault. There we go. All right, so we have this. So 1, 2, 3, 4, 5, 6. This is hex 3-ene. We look at the double bond and we look at the hydrogens. Each vinyl carbon has a hydrogen, and they are on opposite sides. So this is trans hex 3-ene. Here we have 1, 2, 3, 4, 5, 6, 7. This is hex 3-ene. Each vinyl carbon has a hydrogen. They're on the same side. So this is cis hept 3-ene. Sorry if that was loud. I kind of put my cane down right by the microphone. All right. So we're just going to put cis and trans before the name. So if you have, something longer, right, with more substituents, right, so this is dimethyl hex 3-ene. And it's going to be 2,5-dimethyl hex 3-ene. And then we have to decide if they'll bond is cis or trans. Hydrogens are on opposite sides, so that means it is trans. So you just put the trans out front. So you can name the whole molecule and then put trans out front, and that will dictate where you have your, that dictates that your double bond has to be trans in the structure. Now what if we have a case where we don't have a hydrogen on each carbon of our double bond? right? So there's a different nomenclature system for that, right? So when you have molecules that don't have hydrogens on each vinyl carbon, we use the EZ nomenclature system. So we do is you assign priorities to each group that is in your on your double bond, and then you will do and then based on if those if the high priority groups are on the opposite side or on the same side, you will assign it E or Z. Right, so for E and Z naming, use when they're, oh, that's not a T. Not a hydrogen on each vinyl carbon. So in situations like this, where now I only have one hydrogen, right? So for cis and trans, I have to be able to compare a hydrogen on each vinyl carbon. So I can't use cis and trans here because there's no hydrogen on this carbon, right? So there's nothing to compare this hydrogen to. So that's when you use E and Z, right? So to do E and Z, you need to E, right? You have the high priority groups, are on opposite sides, right? So we assign priority to the groups just like we did with stereochemistry. So based on atomic number. So the high priority groups are on opposite sides, and then Z, the high priority groups, that is a dinky I, high priority groups are on the same side. That's right, I said it once before, you might have thought maybe you were like, huh, is this a bad recording? No, same side, they're on the same side. You remember this, Z, high priority, same side, right? So your high priority groups are on the same side. Right, so the nomenclature is pretty straightforward. You just put an E or a Z in front. So you have an E or a Z in parentheses in front of the name. The parentheses aren't always there, so let's do something similar to the one we just did. All right, so the way we assign priority is we want to break our double bond in half, and we're looking at each carbon individually. So we take our H, so we're going to look at our red carbon first, and we're going to compare the two groups on the red carbon. So I've got a carbon, so this red vinyl carbon, I have a carbon and I have a hydrogen. What has higher priority? You said carbon to yourself, good job. Carbon has higher priority. Now, I ignore the red carbon and the groups on it, and I go look at the blue carbon. right? And now I'm comparing a carbon and a carbon. Those are tied. So then I go out the next atom. Hydrogen, I'm comparing a hydrogen to this carbon. What has higher priority? The carbon. So that means this whole chain is 1. Now that I have assigned priorities to the two groups, now what I can do is say, are these on the opposite sides of the double bond or on the same side? So we look at the double bond. I'll leave blue here. Whoa. I look at the double bond, so I'm looking right here, right? This one, the red one and the blue one are on opposite sides of that blue line, right? So these are on opposite sides, so this means this double bond is E. So if we were naming this, it would be 1, 2, 3, 4, 5. So it would be pent to ene, and then it'll be 3-methyl pent to ene, and then E. So it's E3-methyl pent to ene. And again, we number to make sure our ene has the lowest possible number. So we go 1, 2, 3, 4, 5. So you've already got that one named. That's all right. I'm gonna do some melt. All right, so starting, I guess, top left, hopefully, you're looking at it. So longest chain, come on. Longest chain is right here. And that's going to be 1, 2, 3, 4, 5, 6. That's going to be hex. So that's going to be 3-hexene, and then we're going to have a methyl, and a bromo. So we're going to be 4-bromo, 3-methyl. Now I need to assign priorities, so you're going to break your double bond in half. Oh, come on. Break your double bond in half. I could have sworn the red one was highlighted. Okay. That's red one. Break your double bond in half. Oh, yeah. Artsy. All right, we're going to look at the red vinyl carbon first. Right? We're going to compare bromine versus carbon. Bromine has a higher atomic number, so bromine is first priority. And again, we're going to now look at the blue carbon over here. Right? And we're going to compare methyl to ethyl. It's going to be carbon and carbon tied. Compare hydrogen, carbon and hydrogen. 1, those are on opposite sides. So this is going to be E. So E4-bromo, 3-methyl, hex 3-ene. Here, we've got 1, 2, 3, 4, 5, 6. Again, hex, it's going to be 2-ene. and it's going to be 3-chloro. All right, we're going to break our double bond in half. Look at the red carbon first. All right, we're going to say carbon versus hydrogen, carbon wins. Now we're going to look at the other side. Look at the blue carbon, or the blue vinyl carbon. Chlorine versus carbon, chlorine wins. Now compare the two sides. The ones are on the same side of the double bond. So this is going to be Z. Here, we're going to have 1, 2, 3, 4, 5. Pentene. And then we're going to have bromo. And if you remember how to name ethers, this is methoxy. Right? And so we're going to be 2-methoxy, 3-bromo. Come on. Okay. So carbon versus oxygen. Oxygen has a higher atomic number. So that's 1. Then we look at the blue side. Bromine versus carbon. Bromine. The two groups now, you compare them. They're on opposite sides. So this is going to be E. Now for rings under 9 carbon, so less than 9, you do not have to put you do not have to put cis or trans because the only way you can make a ring that is smaller than 9 carbons with a double bond in it is the double bond has to be 6. So here, it is redundant to add cis or trans to this cycloalkane's name. So this is just going to be 3-methyl cyclohexane. Right, we would start numbering here. 1, 2, 3. Right, so you don't have to put cis or trans. You can still use E and Z if it were appropriate. Oops. But again, it's also mostly understood. Right, so if we had this, right, bromo, cyclohexene, right? It's not wrong. Okay, you did see that the red one was highlighted, right? Like I can go to the video and look. Right, this is going to be 1 because I'm comparing it against the hydrogen. And then here, 1, because I'm comparing it bromine versus carbon. This is E. But that's not 100% necessary because, again, there's only really one way that you can put these together. So you don't really need to put the E or Z, but you can. I think of other things we can do here. If you have, again, if you have a group if you have a terminal alkene, there's no cis trans or EZ. So this is just 1, 2, 3, 4, 5. So this is going to be pent 1-ene, be 3-ethoxy. Some of you might be thinking right now, well, what happens if I have alcohols or amines? in addition to a double bond, I don't do that in organic 1. So it's going to be one functional group, one suffix bearing functional group in a name. You're not going to have 2 right now. I leave that for organic 2. So you're not going to worry about that. Every so often I will space out and put one of those with 2 functional groups on an exam, and as I'm grading it, I'll realize like, oh, I don't know how to do that, and you just get free points. So hopefully I won't space this time. So again, terminal alkynes do not have easy cis trains. If you have 2 identical groups on your double bond, man, the pen is fighting me hard right now. The pen hates me. If you have two identical groups on your double bond, we're going to switch to the finger. Right? If you have 2 identical groups, so here I have these 2 methyl groups. There's no E, Z possible. I don't know if the finger is better or not. That E looks like it's making out with a 3 or something. I don't know. It's rough, man. There we go. No E, Z possible. Right? Because if you think about it, you would name this, right? 1, 2, 3, 4, 5, 6. This is hexane. 1, 2, 5, 6. This is hexane again. Also notice I do hexane a lot. Because I just get to 6 and I'm like, yeah, I'm tired. I'm done here. So here's 2-methyl hex 2-ene. Right? If you tried to assign E or Z, right? You'd be like, all right, I'm going to break my bond. Look at my red carbon. I can assign priority over here. I look at my blue carbon now. You can't assign priority. You're like, well, carbon and carbon tied. When we go out, hydrogen versus hydrogen, still tied. Oh, I can't assign priority. So since you can't assign priority to say which one has higher priority, you don't end up being able to assign E or Z. Now, if you think about it, it makes sense on like just like intuitively, because it doesn't matter. These 2 groups here and here are the same. It doesn't matter if I draw the molecule the way I have it drawn. I'm going to redraw it so it's clear. It doesn't matter if I have it drawn like this or if I draw the molecule like this. We're going to draw it the same way here, like the same number of carbons. Hey, we did it. Well, like that, right? Because either way, I'm always going to have this propyl group is going to be beside a methyl group. So if I flip it over, here's this propyl group. It's beside a methyl group. So it doesn't matter how you draw it, the molecule is going to be the same. So you don't have to assign E or Z or cis and trans. Right? We still have the same like count out to assign priority, like so count down a carbon chain. So right, so we have this. All right, so if we have this, so what's our longest chain? Longest chain is going to be starting here. Right, so this is our longest chain. We're going to break. Oh, I should probably write down everything first. Sorry, guys. So we got 1, 2, 3, 4, 5, 6, 7, 8. So this is oc something ene, and we're going to have a methyl and a propyl. Right. So now let's number it real quick. 1, 2, 3. So 3 ene is this 3 methyl, 4 propyl. Okay, so 3 methyl, 4 propyl, oct 3 ene. Now we have to decide if it's E or Z. So we're going to do the same thing we've been doing. Right, so break the double bond in half, which I got a little ahead of myself there. Break it in half. Look at our red carbon. Carbon, carbon, tie. Go down. Carbon, carbon, tied, go down. Carbon, carbon, tied. What's the next atom out here? It's a hydrogen. Carbon, hydrogen, carbon wins. This chain gets higher priority. I do the same thing on the blue side. Get a dot in there. Carbon, carbon, tied. Carbon compared to hydrogen. Carbon wins. This chain gets 1. They're on the same side of the double bond. This is Z. So it's very similar to all the rules. It uses all the same rules that you used for stereochemistry. So hopefully, if you have the stereochemistry relatively down, assigning E and Z will be pretty straightforward. All right. So, yep. I think we're good here. I don't ever use the double bond one too often. I guess this is reasonable to bring. Yeah, we're good. We're good. Okay. So the last thing I guess the last thing before we get into reactions, this will be the last thing before reactions. This should be a good place to stop. Right? Is as I say, I always try to like prove to you guys that this stuff matters outside of just class. So here are some naturally occurring molecules that have double bonds in them. So here's prostaglandin F. The prostaglandins, there's a bunch of them, and they all signal for different things, signal in different ways. And what determines how a prostaglandin works is a combination of the stereochemistry of these alcohols. I can't click on this. It's the stereochemistry of the alcohols around the ring and on the chain and in the methyl groups, as well as if the double bonds are cis or trans. So changing the double bond geometry in concert with changing the stereochemistry of the alcohols makes it so this signals differently. Squalene oxide. Squalene oxide is the basis of all of the sex hormones, so estrogen and testosterone and all that stuff, right? So all of those molecules start out as this long chain with this 3-membered ring that contains an oxygen in it, and then through some enzymatic activity, this will close to the classic ring system that is the sex hormone. So it closes, and I have the technology here, right? So it goes from squalene oxide, and you end up with the classic A, B, C, D ring of your steroids and your sex hormones. So A, B, C, D. I left off some methyl groups just for clarity's sake. But, so this squalene oxide folds up into that molecule, into that structure I just drew. This little molecule here, that's the part of onions that makes you cry. So when you cut onions, this molecule is released. It's based on, this is where I didn't do got a C in biochem. I don't know all my amino acids. That's, total blanket. Don't tell Richardson. Shh, between me and you. I should remember this. Makes disulfide bridges. Do not remember. Anyway, this compound here is what onions give off, and it breaks down into a smaller molecule, and that smaller molecule is a lacrimator, and it makes you cry. Right, and then last but not least, this is singular. It's an allergy medicine, and this number's a little old. I think this is from like 2014. It made $3.3 billion. So it's a lot of dough. And it has this double bond in between these two rings, right? And that double bond is important because it holds the shape of the molecule, right? So being that trans double bond, it holds these rings, the two rings, at a set distance from each other and in a set orientation, and makes it so the molecule is more active. If that were a single bond, it would be able to rotate, and there would be times where those groups wouldn't be in the right orientation to bind to whatever receptor they need to bind to. And so the molecule wouldn't always be on and ready to react or ready to bind. And if it were a cis double bond, it would maybe be locked in the wrong conformation totally and just not work at all. So having that double bond there locks the molecule into a fixed position that allows it to react. And with that, I think that is a pretty sweet place to stop. Yeah, because then we go right into reactions next. So this is a good place to stop. It's a good place to want to think through. So there you go. This is a super chill lecture. I found out you guys can't see me with this recording setup. So got to come in a sweet Star Wars t-shirt, some shorts, just relax and chill. So hopefully this gets us caught up a little bit, and we'll come in and we'll jump into reactions next time we have class. So thank you very much.